Information up here with which I expect you to be concerned. How many of you are taking a lab final? Lab finals tomorrow.
I'm going to.
That's it? Just curious. You know, you don't have to. You don't have to take any exam. You know, if you like zeros. Lab finals tomorrow. Main lecture auditorium. Tee off time 7 o'clock. Your TAs will be there to conduct the exam. 45L students will also be there. So what? We got a lot of room. This is only about 40 students or 50 students total who will be dealing with the 45L, 46L exams on a combined basis. Pardon me. I expect to publish bonus quiz 3 this afternoon. I worked on it this weekend, just about finished it yesterday. I want to think about it a little bit more, and I'll do that this afternoon and immediately publish thereafter, at the latest tomorrow. But you're going to need to know the stuff we are presently talking about in order to be successful with the bulk of bonus quiz 3. As you know, I'm sure, we're getting ready for the last waltz. Exam 4, Part 1, will be operationally somewhat different than exams 1, 2, 3. There'll be considerably greater amount of points available. And rather than operating the first session during the discussion period on Friday, this week, we'll use the discussion period for regular class gathering, probably the bulk of which will be for exam review. And as the syllabus tells you, Part 1 of the last exam will be Friday evening. 2 pages. They give you 3 hours. Then Part 2 will be the following week, Tuesday evening. 2 pages again, 3 hours. You got a lot of time to express yourself. Part 1 will contain questions and problems from stuff we've already done. After I compose Part 1, I'll tell you which questions and problems to go back and look at from past exams. And bonus quizzes too, if such applies. I prefer to do that rather than just saying everything we've done is fair game. We've done a lot. And this is tough, challenging stuff. I repeat, it's not me that's tough. It's chemistry that's tough. I just happen to be of a mind to show you what chemistry's like. So, there's the operating schedule for Part 1 of Exam 4. We'll say more about Part 2 as the week proceeds. Remember, please, next week we have 2 lecture classes, Monday and Tuesday. Also, along with bonus quiz 3, I will ask you folks to submit an evaluation form regarding your discussion instructor with whom you have been on Fridays for this term. That will be in a particular fashion viewed by me as your passport to get credit for bonus quiz 3. Because I like you to participate in this evaluation process, so we get feedback from you folks regarding what you've thought about the course and about the people who've attempted to help you learn the material. Same thing applies to me in the course evaluation, but that's strictly an online activity. I really think the university made a mistake in making this strictly an online activity, but it's really not for me to say. But I do object that the university does not take the lead in getting students to participate in the evaluation process, given that it's now strictly an online activity. Still, they expect each of us, the individual faculty people, to make an appeal to you and believe that's going to be good enough to get you to participate. I've not seen any participation extent yet which it gets up to 40%. This is your chance to say something. I invite you to take this chance. Whatever you want to say is held in confidence and placed under sincere consideration. What you think. Tell us what you think. Tell me what you think. There's no holds barred. Say whatever you like. And so we proceed. Again with chapter 24 being the aim. But we're still finishing the stuff at the end of chapter 23 on the unusual complex nickel tetracarbonyl, simply because these considerations provide such a strong springboard into chapter 24 stuff, because nickel tetracarbonyl is in fact a transition metal complex. Complex of nickel as the Lewis acid, the central metal in this complex, with carbon monoxide ligands. Ligand again being the transition metal chemist's name for Lewis base. What happens when the Lewis base interacts with the Lewis acid? What happens when the carbon monoxide molecules meet with nickel atoms to form this stuff? A sigma coordinate covalent bond is formed. The Lewis base ligand molecules carbon monoxide supply per molecule a non-bonding electron pair from the carbon end strictly of the CO molecule, which then becomes a bonding pair by taking occupation in an empty valence orbital of nickel as it becomes coordinated with the carbon monoxide molecule. We examine the electron configuration diagram for this, recognized that nickel tetracarbonyl shows nickel as an sp3 hybridized atom, which provokes us to argue that this complex is expectedly tetrahedral, which it is. We also recognized that nickel itself is a paramagnetic material. But when this complex forms, paramagnetism disappears. So the bond formation interaction is strong enough to get the nickel atom to change its electron configuration when the complex is formed. Indeed, the 4s electron pair, in conjunction with the 3d8 configuration for nickel atom by itself, converts to a 3d10 configuration. The 4s electrons, as if by magic, jump back into the 3d sublevel. Because indeed, by analyzing the electron configuration for the complex, the only way this complex could be diamagnetic is if the configuration for nickel, which we just mentioned, was in fact the configuration developed. 3d10 4s0. So now the 4s orbital is available to accept a non-bonding pair from a carbon monoxide molecule as a coordinate covalent bond is formed. And if to that we also consider the 4p sublevel, which is empty, we got 4 ligands, so 4 sigma coordinate covalent bonds are formed. We need 4 empty valence orbitals from nickel. The electron configuration diagram analysis showed us it's 4s and each of the 4p orbitals in the 4p sublevel. That gives us sp3 hybridization and tetrahedral geometry. And also shows a configuration in which all occupied orbitals are filled. So no paramagnetic carried. From this, we went on to say, nickel plus 2 is clearly a stronger sigma bond former than nickel 0. Nickel plus 2 shows a natural coulombic attraction for electron density. Nickel plus 2 makes no stable complexes with carbon monoxide. But nickel 0 does. What's this tell us? This tells us that the stability of an unusual complex like this, unusual because nickel is in a zero oxidation state. The stability of a complex like this is not attributable to the strength of the sigma coordinate covalent bonds which formed when the complex was formed. It's instead attributable to the strength of the pi bonds which form. How do the pi bonds form at the coordinate covalent bond site? The pi bonds form as a consequence of the metal now behaving as the Lewis base. The metal using valence d electron density. Does nickel 0 have an abundance of valence d electron density? Hey, it's 3D sublevel is filled. It's 3D10. So it's loaded with valence d electron density. And can we well expect nickel 0 to be willing to share, so to speak, this 3D electron density to make these pi bonds? Why not? It's zero oxidation state. It doesn't exert a Coulombic restriction on sharing this electron density. So we're looking at a role reversal to make the pi bonds. The complex metal in a complex like this supplies the electron density to make the pi bond. So in that respect, pi bond formation invokes the metal behaving as the Lewis base. And the ligands behave as the Lewis acids. So now we have to answer the question, how can a molecule like carbon monoxide make pi bonds? And with that, we looked at the Lewis structure for carbon monoxide and said, now you got to realize that Lewis structures have one significant shortcoming. They show you valence electrons, Lewis structures. What do they not show you? All the valence orbitals, which are part of the valence environment of the species. Well, for carbon monoxide, all you got to do is recognize that carbon and oxygen are each from period 2, so they each have 4 valence orbitals. So we're looking at a species which has got 8 total valence orbitals. And the Lewis picture for carbon monoxide shows that all these valence orbitals are not occupied, which means some of these valence orbitals are still there and they're empty. The remaining part of the puzzle then is, are these empty valence orbitals possessed by carbon monoxide capable of pi bond formation? And to pursue that, I told you all to look at page 25.4. Do that right now. Take a look at the molecular orbital energy level diagram for carbon monoxide. If time permits, at the end of this week or the start of next week, we'll talk about how a molecular orbital energy level diagram for something like carbon monoxide can be developed. It's really pretty simple. You start by realizing carbon, like oxygen, as we've already noted, each has 4 valence orbitals. So you start putting together these valence orbitals by an arithmetic method known as linear combination. Linear combination is the simplest possible arithmetic method which we can use. What does linear combination involve? Do you know? Addition and subtraction, that's all. Addition and subtraction. The rule of the road is, when you add valence orbitals, you get a bonding molecular orbital. When you subtract valence orbitals, you get an against bonding molecular orbital. In this diagram that you're looking at, you'll see against bonding molecular orbitals identified by an asterisk. They're always higher energy than bonding molecular orbitals. Nothing so surprising about that. And when you look at this diagram that you're now looking at for carbon monoxide, you'll see that the number of molecular orbitals in the diagram derive from the 2s and 2p atomic orbitals of carbon and oxygen respectively equals 8. Because each kicked in 4 atomic orbitals. So 4 plus 4 is 8. So you're going to look at 8 molecular orbitals in this diagram. And a molecular orbital energy level diagram is populated with electrons in the order which I would expect from lowest energy to highest energy. Go from bottom to top. And so you see, in this diagram for carbon monoxide, Because carbon monoxide shows 10 valence electrons, right? 5 electron pairs. That's what the Lewis structure shows us for carbon monoxide molecule. We've already looked at this. Well, if you got 8 molecular orbitals, how many of these orbitals are filled up? 10 valence orbitals. No unpaired electrons. So for carbon monoxide, you got 5 electron pairs, right? How many orbitals we need to provide parking place for 5 electron pairs? 5 orbitals, right? You can put 1 electron pair in every orbital. That means the molecular orbital energy level diagram for carbon monoxide, which you're now looking at, shows 3 empty orbitals. Nothing fancy about this. It's really a pretty simple game arithmetically, at least for 2 atom species. Okay? And when you look at these orbitals, given that they are derived from s and p orbitals, we know when all the p orbitals from a sublevel of an atom, like the 3 p orbitals from the 2p sublevel for carbon, combine with the 3 p orbitals from the 2p sublevel for oxygen, how many molecular orbitals are you going to get? 3 plus 3 is not too hard. 6. And of these 6 orbitals, 3 will be bonding and 3 will be against bonding. That's just the rules of the road. When you add these orbitals together, if it's an even number of orbitals, the number of bonding orbitals and the number of against bonding orbitals are the same. The bonding orbitals will be lower in energy. All right? And when you put together p orbitals, 3 from one sublevel for one atom, the other 3 from this p sublevel for the other atom, how many sigma overlaps can you get? You know what a cluster, a sublevel of p orbitals look like? You did this in 2045. There's 1 p orbital. There's another p orbital. And sketching the 3rd p orbital is clumsy because this is a 3-dimensional construct and I only got a 2-dimensional surface on which to draw this. We got an axis this way, we got an axis this way, and the other axis is depicted like this, but this axis is perpendicular to the drawing surface. So you got 1 p orbital lobe sticking out this way, and the other one is behind the drawing surface. That one's not easy to draw. While at the same time having you recognize that this is a 3-dimensional projection. You usually do it like this. But now the picture looks like hell, doesn't it? So you got to use your imagination. Now this direction, the geometers and the chemists each agree that this direction is taken as x. And simply because alphabetically x comes before y and z, with x, y, z being the most common labels used for what? Cartesian coordinate reference axes, right? You know about Cartesian coordinate reference axes. You've been using them ever since high school geometry class. Just 3 straight lines which project in space at 90-degree angles with respect to each other. 3 straight lines which share the geometric property of being mutually perpendicular and intersect at a position in space called what? Origin. How about that? So you heard all this stuff. So if you draw the axes without the orbitals, you got something that looks like this. X is taken as the axis along which the sigma bond is formed. Now I can define this any way I want, but that's the way it's usually done. It's because X comes before Y and Z. Well, that means this p orbital can overlap with the same kind of p orbital, another px orbital from the other atom, and that gives me a sigma bond involving p orbitals. Principal characteristic of a sigma bond is 1 overlap region. And the strongest sigma bond is that which lies on this imaginary axis that interconnects the nuclear positions. Okay? What kind of overlaps can we make with the remaining p orbitals from the sublevels of each atom, respectively? Well, you got py with py and pz with pz. Now, chemists, unlike geometers usually say, we'll call this direction y. But transition metal chemists, and that's not what we're talking about, they call this direction z. It doesn't matter, it's arbitrary. So we got to agree. So I ask you to accept that. When you look at chemistry books, this direction is z. So what? By default, then, that makes this direction y. Arbitrary and capricious, it doesn't matter. You know, I could call this x. I could call this q. Who cares? It's just a label. It doesn't mean anything. The point is to realize when py and py overlap, and when pz and pz overlap, what kind of overlap do I get? Pi or sigma? Pi or sigma? Pi. Because for pz with pz, I got two orbitals which are oriented in space such that their lobes are all mutually parallel. So when they overlap, this is what I get. Two overlap regions, pi bond. For the py, one is here, the other one is here. There's the two overlap regions. Again, difficult to draw on this surface because these lobes are perpendicular to my drawing surface. Okay? So when you're looking at this diagram, are you seeing that some of these against bonding pi-type orbitals, pi-type, because they involve atomic p orbitals overlapping in pi fashion. Do you see these pi-type orbitals empty? When you look at this picture? Okay. So, from a theoretical standpoint, we are arguing that metal d electron density populates those empty against bonding pi orbitals. But in this case, remember, the against bonding character applies to the bonding in the carbon monoxide molecule itself. It doesn't apply to the bond formation interaction between nickel and the ligand. So we get a bond between nickel and the ligand. The nickel uses the d electron density to take occupancy in these empty pi-type molecular orbitals derived from p orbitals in the carbon monoxide molecule. Okay? Now keep in mind what I said. That anti-bonding property of the orbitals that we're now populating with d electron density is a property that relates only to the carbon monoxide electron environment. Question. When metal d electron density populates this against bonding molecular orbital, which you're looking at in this picture, what do you think happens if all this fancy story I'm telling you is true? When carbon monoxide complexes with nickel to make this stuff, if this fancy story I've told you is true, what do you think happens to the strength of this carbon monoxide molecule bond? We're not talking about the strength of the bond between the ligand and the metal. We're talking about the strength of the CO bond itself. If the story I told you is true, what happens to the strength of that bond? Because the orbital that got populated to make the metal to ligand bond is against bonding for the ligand itself, right? That's what the picture shows you. What happens to the strength of this bond? When that orbital that you're looking at in the diagram, when that orbital gets populated, what happens to the strength of this bond? Because for the ligand, that orbital is against bonding. And if you populate against bonding orbitals, you weaken bonds. So guess what? It's almost by magic, but this is how we know these stories we tell you have validity. When this complex is formed, the carbon monoxide molecule bond itself gets weaker. Keeps with the story, doesn't it? Interesting. Now the net payoff is that the bond strength, the pi bond strength between nickel and carbon monoxide exceeds the weakening of the carbon monoxide molecule bond itself. But that carbon monoxide molecule bond itself gets weaker when complexes like this form. And that's why we believe these stories are true. Because the facts tell us they're true. Interesting, isn't it? Because if I tell you a story and the molecules don't behave accordingly, I have to change the story. These molecules, as we remind you, they don't care what we think, they don't care what we say, they don't care what we calculate. They never have and they never will. But they're the stuff of chemistry. And we have to cook up stories which explain their behavior. Because they don't behave in accord with our stories. They don't care what we say. So we have to be clever enough to figure out how they're operating and cook up stories which keep with their behavior. All right. Now then, we read the statement then. Stability of all complexes like nickel tetracarbonyls attributable to pi bonding involving the metal. The electron density occupying these kind of orbitals for the ligand. What kind of orbitals are these kind? Empty. Pi-type orbitals. You're seeing the picture on page 25.4, which applies to carbon monoxide. Okay? Note that these complexes show metal in unusually low oxidation state. 0 or even negative oxidation state. We'll look at some more examples in just a moment. Now then, to get a handle on why we can expect the overall electron configuration for a complex like this to be stable, we have another neat gadget. In 2045, when you talked about bond formation, did you not, practically speaking, all the time argue that when atoms engage in bond formation, they do so from an electron configuration standpoint in an attempt to do what? Achieve what kind of configuration? Noble gas. Noble gas, you betcha. Well, let's see if that applies to this. Here's our complex. The task I assign to you right now is simple. Tell me the total number of valence electrons, which are part of the valence environment of this complex. Well, let's go back to the diagram. There's 3D. Remember the diamagnetic character of the complex? That told us that the 4s valence pair that the nickel atom has reverts back to becoming part of the 3D, or taking occupation in 3D sublevel on complex formation. And then, by forcing that 4s valence pair for the nickel atom to take residence in the 3D sublevel, provoking the diamagnetic character which results, the 4s orbital becomes open. So that's a parking place for an electron pair from one of our carbon monoxide ligands. Well, we got 4 carbon monoxide ligands. We're going to form 4 sigma covalent bonds, coordinate covalent bonds. So we need also to use the orbitals from the 4p, empty valence sublevel for nickel. So there again, given that we drew this picture previously, is a picture of the occupied valence orbital diagram for nickel tetracarbonyl. These are the metal electrons. These are the electron pairs supplied by the 4 carbon monoxide molecules. Count the number of electrons you see in this picture. You get 18? You get 18, don't you? Nothing fancy about that part of the puzzle. So we look at the next question. Question 2365 in the notes. Consider krypton. Because krypton is the first noble gas atom immediately following the first row of transition metal atoms. What do we recognize about these transition metal atoms? Their chemistry is elaborate, rich, complicated relative to non-transition metal atoms because they have a mixed bag of valence electrons. 3d and 4s for the first row, 4d 5s for the second row, and 5d6s for the third row of transition metal atoms. So by analogy to transition metals, how many valence electrons can we argue 36 krypton to have? 18. 3D, all filled, so that's 10. 4s, filled, we're up to 12. And 4p, filled, so we're up to 18. 3D, 4s, 4p. All arguable as valence electrons for krypton. Well, we're just making an analogy to the valence electron configurations shown by these transition metal atoms. So we have a magic number. Magic number is 18, because that corresponds to the valence configuration for krypton. Argument. When we look at the possibility of forming any unusual complex in that the complex metal is in a low oxidation state, like 0 or negative, in order to expect this complex to show stability, we analyze its electron configuration and look for what number? 18. And if it's 18, we can expect it to be stable. And if it's not 18, we shall expect it not to be stable. And the best part of it is facts bear this out. If we get the 18 electron count for complexes of transition metals, where again the transition metal is an unusually low oxidation state, the stability of the complex is attributable to this pi bond formation, which we've already described. We can expect this thing to be stable. And if we don't get 18, we expect not stable. So let's go back and take a look at question 2366. Nickel tricarbonyl. Nickel pentacarbonyl. These do not exist. How many valence electrons would this show? Well, you got one fewer carbon monoxide ligands, don't you? So this would show 16 valence electrons. Too short a krypton. Doesn't exist. This would show 20. Doesn't exist. Well, let's play this game now for an iron complex. 2367. Iron in the 0 oxidation state forms a stable complex with carbon monoxide. Tell me the correct formula for this complex. In order to do that, you got to tell me the numerical value for X.
X is 5.
X is 5. I have a vote for 5. How many concur with this vote? Why do you say 5? Does that give us 18? How about that? Now then, let's play the electron configuration analysis game. First, we'll take away all the electrons, but leave the orbitals. Because iron is also in period 4 like nickel. So it's going to have the same collection of valence orbitals. Let's start with the iron atom. How many valence electrons for the iron atom? Number 26. How many?
8.
Nothing fancy about that. So first, let's write the electron configuration for the iron atom, all by itself. No complex formation yet. 1, 2, 3, 4, 5, 6, 7, 8. And I should have put these in first, because this fills before any d electrons are added. But as soon as the d electrons are added, then this gets more stable than 4s. That's why the 3d sublevel as I've drawn this diagram, since this is an energy diagram as well as an electron configuration diagram. 3D is lower energy than 4s. But that doesn't happen until you start putting electron density in 3D. All right? Now here come the carbon monoxide molecules. Well, we're counting here 8 electrons, right? And we've already recognized each carbon monoxide molecule will supply 1 electron pair to make 1 sigma coordinate covalent bond with iron. And if we're going to get up to 18, then we got to have 5 carbon monoxide molecules to put 10 more electrons into this picture, because that'll give us 18. All right? Well, on so doing, here come the carbon monoxide molecules right now. That's charge. Here they come. We're going to make bonds. What's going to happen in this 4s pair? Put another way, do you expect this stuff to be paramagnetic or diamagnetic? Again, iron by itself is quite paramagnetic. It's got 4 half-filled d orbitals. That's the iron atom by itself. But this stuff is diamagnetic. Just like nickel tetracarbonyl. So here comes this magic again. These come over here. And what happens to these two? If this is diamagnetic, these have to pair. They didn't pair, the thing would be paramagnetic. Okay? Now let's see what empty valence orbitals we got. Here come the 5 carbon monoxide molecules. Bond 1, bond 2, bond 3, bond 4, bond 5. Which valence orbitals got occupied? D, S, and all 3 of the P's. So there's the orbital label, hybrid orbital label, DSP3. And notice for this hybrid label, D is written before S and P. You talked about this kind of stuff on Friday. Because D is from energy level number 3 and S and P are from energy level number 4. If you had an sp3d hybrid, then the d orbitals would also be from energy level number 4 or the same energy level as the S and P orbitals. But this scheme tells us the d orbitals are lower in energy than the S and P orbitals. This is said to be an inner orbital complex. Inner orb complex, just language. Inner, in that. The d orbitals are lower in energy. They're inside the S and P orbitals. That's what this means. All right, there's the hybridization. You've seen this hybridization before. What kind of geometry do you attribute to this hybridization? What do you say it is? Trigonal bipyramidal. So I'll write down trig bipier. So now we're going to go to the laboratory. We're going to take a sample of this stuff and we're going to do a structure determination on it. We want to see if this fancy story we cooked up holds water. And what do we find out? We found out A, this is diamagnetic, and we find out B, it's trigonal bipyramidal. How about that? So we go pat ourselves on the back and say, oh, this fancy story is good. Because it keeps with the facts. That's why it's good. All right, look at 68. You have to crane your necks 90-degree angle. Big strain. Heck, you got young necks. Me, I'm older. I refuse to be called old. I'll be called older. I'll never accept old. Hell with that. That's tantamount to committing myself to the absolutely worst thing that any person in my shoes could do. There's one nasty, rotten, filthy 4-letter word in my language. It's called retirement. Ain't no way. They might take me out of here horizontally, but they'll never take me out of here on my own volition. Retired, never. You think I worked all these years to get to this point and then give it up and go fishing someplace? I mean, I might like the fishing for a day or two because I like fishing. But for a day-by-day activity, put me in a rubber room in 2 weeks. I'm not doing that. Retire. That's disgusting. I can't think of anything more horrid and disgusting than that. Ain't no way. That never happened to me. Now then, Let's go back to this one. I've offered you the formula for 3 possible carbon monoxide cobalt complexes. One of these formulas represents a stable complex. Which one do you believe it is? You tell me, and I'll write it over here. I'll put down this part. So the only part of the puzzle you have to fill in is what goes up here. Is it plus, 0, or minus? And to answer this question, all you got to do is count. Cobalt, by itself, atomic number 27. Did you recognize that any atom with an odd value for Z, its atomic number is not an even number, has got to be paramagnetic? I hope you learned that in 2045. How the hell can you have all the orbitals filled if you got an odd number of electrons? So you got 27 as the total number of electrons. How many valence electrons for the cobalt atom all by itself? It's between iron and nickel. The answer shouldn't be too hard to get. 9, right? If iron's got 8, nickel's got 10. You subtract 9 from 27, you get 18, don't you? And then you got the argon configuration. So cobalt atom all by itself got 9 valence electrons. So how many more valence electrons you got to put in there to have the magic number of 18? Boy, that's really tough. 18 less 9 equals cipher, multiply, square roots, fancy formulas. 9. So we're going to bring in 4 carbon monoxide molecules. That adds 8. And then we're going to add 1 more electron to create a negative charge, aren't we? Here it is. So for this complex, which of these 3 cobalt complexes of carbon monoxide is the only one that's stable? We now have the metal in what kind of an oxidation state? Negative. How about that? More interesting stuff achievable by this transition metal chemistry. Coordination chemistry of transition metals. We now find metals stable in negative oxidation states. You don't see that for these non-transition metal materials. We're seeing it here. Interesting. Interesting in the main because it's true. All right? So let's do 69. This is a mixed complex in that it's got 2 different kinds of ligands. In this complex, carbon monoxide, CO is carbon monoxide. But NO is not an odd electron species. NO is NO+. Nitrosonium cation. I think it's nitrosonium. I don't know. I don't care about its name. When I got its formula, I got what I need. NO+. On your paper right now, Lewis picture for NO+. I trust you recognize the Lewis picture just like carbon monoxide. The only difference between being that this is a cation, an unusual cation. Ammonium ion, another unusual cation. Because just about all cations have elemental components. Metal components, pardon me, have metal components. Because the metals are electropositive relative to the non-metals in general. But here, unusual cation. Tell me, which end of this species do you expect to be the donor end? Which non-bonding pair is used to make sigma-coordinate covalent bond? Or is it either end, depending upon the environment? If you're going to bet your last buck on this, how are you going to bet? I got a bet for nitrogen. Any more bets for nitrogen? Any bets against nitrogen means you're betting for oxygen. Hey, this thing shows plus on oxygen. Would that make oxygen a good donor? Hell no. Something plus. They don't want to share electron density with anything. And how do the electronegativities of NNO compare? Oxygen is of greater electronegativity, right? That means this is a better electron pair sharer than this. Because this, with the greater electronegativity, coupled with the plus charge, stabilizes this non-bonding electron density far more effectively than this non-bonding electron density is shared. This is the only pair ever used by NO plus to make a sigma-coordinate covalent bond. Now let's ask another question. Something about the sigma donor strength of this. Do you think this is an effective sigma donor? A good sigma donor? Do you think this thing makes fairly strong ligand to metal sigma-coordinate covalent bonds? Yes, no, or maybe, because you can't tell. No, it's weak sigma donor. Is that how you vote?
Yes.
All right, we had to vote for weak sigma donor. Anybody supporting this vote? I'm supporting this vote. This thing is composed of atoms which are appreciably electronegative, aren't they? It's also plus. The whole thing is plus, not just the oxygen atom. And by induction, this atom says, hey, I don't like you sharing this valence electron density with something else. This is a lousy sigma donor. You guaranteed that any stable complexes with this as a ligand are attributable to what kind of bonding? Pi bonding, from metal to ligand. Do you think this will be a good pi bond former? Isn't this plus? Doesn't its component atoms have appreciable electronegativity? Will this then not attract effectively by the electron density to make pi bonds? You betcha. Hey, we're just sizing up the facts that we've already paid attention to and applying it to this particular species. Let's ask one more question about this. What do you think about this bond strength? How do you think the bond strength of this compares to the bond strength of this?
Great.
Which one is stronger? This one's stronger. Tell me why. This is the strongest bond known in the world of chemistry. The triple bond in the NO plus cation. Give me an argument which tells me why this triple bond is stronger than this triple bond. What property of an atom stabilizes valence electron density? Electronegativity. Is the composite of electronegativity of these atoms greater than the composite electronegativity of these atoms? Because N is more electronegative than C? You betcha. So these bonding electrons are stabilized to a greater extent than those bonding electrons. Okay? Take a look again at page 25.4. That's the molecular orbital diagram for CO. So we'll put this down. Consider MO diagram for NO+. You looking at the diagram? Are you recognizing as you look at this diagram that that's an energy diagram? It doesn't just show you the orbitals, it shows you something about their energies. If you want to draw the MO diagram for NO+, compositionally it's going to look just like this picture, because you got the same number of molecular orbitals, 8. Because you're again making a diagram from period 2 atoms. But what will happen to the energy of the MOs you see in the picture you're presently looking at? If you're going to now say, I want this picture to represent the MO diagram for NO+. What's going to happen to this diagram, energy-wise? What's going to happen to the energy of the MOs in this diagram? If I want it to represent the MO diagram for this thing. Those energy levels for the MO diagram are going to stay the same? Going to go up? Going to go down? It doesn't stay the same. You've got to go up or down. Somebody said up. Any more up? How about down? Now we got to vote for down. Most people not wanting to vote. How often I've seen that behavior before. Minus 83 trillion Avogadro numbers of points on the last exam if you didn't vote. You better live a few lifetimes to pay that one back. Hey, did we not argue that this triple bond is stronger than this triple bond because these atoms have a composite electronegativity greater than this? That means the MO energies are going to come down. They're going to be more stable. Hey, you take the stuff we've been talking about and let it talk to you. We really are not doing anything new or fancy. We're just expanding on the stuff you've been talking about since 2045. That's all we're doing. If you let it talk to you, it's telling you a hell of a lot. That's what I try to get the 2045 people to do. Have these people let this stuff talk to them. They need to memorize a damn trend for electronegativities, and that's the question on the exam. That's worthless. 2-year-old can do that. There's no understanding involved in that. That's what I tell them. Unfortunately, they haven't listened to me yet. That's why I told you folks, if I had my way, every entering freshman would take 2045 with me, period, no alternatives. And we'd either learn it or we wouldn't get through. Because that's what I want. Learning! That's where it's at. Understanding. Recitation of information is an encyclopedic activity achievable by any dunderhead. Jeopardy winning. Garbage. Where's the understanding? I want to know the answer to this question. I look it up in a book. I want to pack my head with ideas and thoughts. Turn your head into an encyclopedia. I mean, there's some value in that. Not nearly that which is achieved by understanding. In any case, back to peaceful nature. We go to this question. This is another takeoff on the 18 electron count and population of the electron configuration diagram for complexes of transition metals where the transition metal is in an unusually low oxidation state. Can we expect any transition metal complexes where the metal is in an unusually low oxidation state to be square planar in geometry? Now, I don't know as yet that you've done much talking about square planar geometry. Do you know the hybridization scheme? which goes along with square planar geometry?
SP3D2.
That's octahedral.
SP3.
SP3 is tetrahedral.
Isn't square planar geometry that's related to octahedral?
What is that?
Like, isn't square planar just an octahedral with two non-bonding pairs?
I agree that's a square planar species, but that has sp3d2 hybridization because you still got 6 electron pairs in the valence environment. For this, we're only going to have 4 electron pairs in the valence environment. Okay? Well, let's look at the diagram and see if we can provide some understanding of why the hybridization scheme is what it is. As we have done before, here are the orbitals. Now let me show you an orbital picture. For which the geometry is pretty simple. Why is the geometry simple? This thing is square planar. We don't have three-dimensional physical quality. We don't have two-dimensional physical quality. So we can quite adequately represent a picture. We can draw a picture of a square planar species on the board because this is two-dimensional. And I don't need 2 dimensions to show a square. All right? So I'm going to pick this axis is X and this axis is Y. Okay? And if my metal's here, and here we'll put down LIG for ligand. Is that square planar? Square planar? Okay, that's square planar. Now then, when I make hybrid orbitals, have you recognized that there's one type of orbital that's always involved? What is that orbital?
S.
S. Why? Why is the S always involved?
One of the highest penetration.
In any energy level, which orbital is most stable? S, isn't it? Well then, when you start talking about bonding, you better always keep in mind the S. But you only got one of them. So the orbital hybridization scheme we're looking at is going to have a single S orbital. Now then, let me tell you that of the p sublevel, for which there are 3 orbitals, or from the p sublevel, we're only going to use 2 p orbitals. And traditionally, we distinguish between the p orbitals that are part of the same sublevel as px, py, and pz. Because their orbitals are mutually perpendicular. And so the simplest way to make geometric reference to them is use Cartesian coordinate axis set, which bear the labels x, y, z. Okay? If we imagine that this is our complex and it's lying in the xy plane, which of these p orbitals are going to be used to be part of this hybrid we're going to construct for this square planar thing? Well, are we going to use px and py? Because they're in the square plane. And if this is the x-axis, then I got a p orbital here, and I got another p orbital here. They're aiming right at the ligand, so I can get effective orbital overlap. So it's s, px, py. All right? Now we got one more activity to engage in to complete this hybridization game. I want you to go to chapter 24. And let's see, where's the page? There we go. Page 2430. Go to page 2430. On this page you see an artist's illustration of all the orbitals in the 3D sublevel. I stole it from a textbook someplace. I don't give a damn. For the purposes of learning. When it comes to learning, nobody owns anything, as far as I'm concerned. Which of these d orbitals do you expect to be part of this hybridization scheme? If we have argued that the square planar complex lies in the XY plane and the ligands themselves lie on the X and Y axes respectively, tell me the label for the d orbital. I got to vote for dx squared minus y squared. Do you see that the pictures show you that the dx squared minus y squared orbital, A has its orbital lobes in the xy plane, and B has its orbital lobes skewered right through the middle by the x and y axis respectively? You see the picture showing you this? Then that's the one we want. And this dx squared minus y squared. It looks like the two p orbitals put together like this, doesn't it? So there's our hybridization scheme for square planar. So shorthand, it's sp2d. Or if we have the d orbital lower in energy than the s and p, then it's going to be sp2. Either one. sp2d or dsp2. Okay? Now let's go to our orbital diagram. Because if we're going to use from 3d, 4s and 4p, a d orbital, s orbital, and two of the p orbitals, because those are the orbitals in which the incoming ligands, of which there will be 4, will each supply a non-bonding pair to make a sigma coordinate covalent bond. All right? D, S, P, and P. Those are the orbitals occupied to give us dsp2 hybridization. Okay? Can this possibly contain 18 electrons? And the answer is no, because this thing is always going to be empty. Statement: under no circumstances can a stable transition metal complex with the metal in an unusually low oxidation state, we're always looking for this magic number of 18 electrons like krypton, can never be square planar. Never. Because you'd have this valence p orbital unoccupied, which means you could never have 18 total valence electrons. We'll pick it up from this point tomorrow.